Hey everybody, it's the traditional mic check. Let me know if you can hear me. And if you can't, oh no, it's definitely your setup. Adjust your speakers. I'll see you in 5 minutes and 47 seconds. Hey everybody, welcome to Goldendale Observations number 10. You might notice that I'm wearing some festive colors because this is the first weekend after the winter solstice, and there are a number of famous holidays associated with that time of the year. I hope you guys got lots of presents if you observe one of those holidays that involves gift giving. Tonight we'll be talking about a certain famous fellow, or rather where he lives, the guy that gives out those presents. And we'll be talking about what's above his house. We'll also be talking about how ironic it is that we think he lives where he does because he probably couldn't, because it's not a very safe place to live. We'll talk about that in a minute. Before we talk about the North Star, which is what our topic is tonight, I would like to interrupt the show again, like I did last weekend, with some information about the Great Conjunction. I hope that some of you got to see it on Monday the 21st. Please indicate if you have on the chat. I know that all of you didn't because the weather was pretty bad that day. For example, it was quite bad here, although we did have a few opportunities to see it. The day after, for example, and the day after was pretty good. However, even though it was fairly clear, the seeing conditions, the atmospheric conditions, were quite awful. So I wasn't able to take any sharp images of the planets, although I do have a very low quality image to share with you in a second. I also have some video to show you. So yeah, okay, see someone else said on the 22nd you saw it, good. Not on the 21st, no. Anyone else see it on the 21st? Lucky you if you did. I've been telling people if you saw it on the 20th or the 22nd, it was almost as good. They appeared almost as close, so you didn't miss much. I was really kind of disappointed by how many people were getting depressed about missing it on Monday. I'm like, guys, it really won't look that different. And part of the reason they were sad is because they had heard it was going to look like this, glorious star in the sky, which is what I was talking about on the episode number 8. That's not, of course, what happened. You just had two fairly bright planets appearing near each other. In the case of Jupiter, quite bright. So, I watched it on TV. That's good. Overcast here, yeah. Not only was it cloudy here, it was also raining, and it was angry. There was so much wind. There was this beating rain, and very cold, very close to freezing rain, so not friendly conditions. All right, so before we start talking about the North Star, and by the way, I expect this to be my shortest show yet. That's probably good news for a lot of you. I'll show you the pictures I took. Here is an unimpressive image. Hold that thought. This was taken through our 6-inch refracting telescope at the observatory. Now, I could have processed these properly. I could have taken thousands of frames via video and then put it into what's called a stacking program to compare the good and the bad and get a sharp image. But I discovered even after doing that, the image quality was not good because, again, the seeing conditions were just awful. For example, you couldn't see any details in the planets. But we could see the general shape, for example. If you look, you can see Saturn's rings there. Of course, we have mighty Jupiter. And what are these 4 dots? Someone tell me, what are these 4 dots, guys? Someone tell me. This was on the 22nd, by the way. Anybody know what these 4 dots are? Moons, yep. Those are the famous Galilean moons. Jupiter has many more than that, but those are the easy to see ones. Those are the ones that can be seen even with small telescopes or binoculars. And I wanted to reveal them in this exposure. The most distant moon is Callisto, and it's not that far from where Saturn was in terms of distance from Jupiter the day before. So Saturn moved about this much. I hope some of you got to see it with magnifying optics. And by the way, if you still haven't, you can still see both objects in the eyepiece of a telescope. You just need to use a little bit less magnification. Imagine that. Now let me show you a little video. This is time-lapse from that same day. All right, so this was from the observatory. As you can see, it wasn't perfectly clear, but we got to see something. And there is the pair setting. And if you look, you can even see the moons. This is only 200 millimeter lens, and yet even at 200 millimeters, we're able to make out the moons of Jupiter. So again, this was on Tuesday the 22nd, not on Monday the 21st. Before I get down to the North Star talk, are there any questions about the conjunction that may have come up over the last few days? I'm going to answer at least one question about the conjunction before I start the show about the North Star. So have at it. Anybody? This will be your last chance to talk about the conjunction which has been on everyone's mind and continues to be on everybody's mind. Anybody? Someone says it could see Saturn unaided. Yeah, that's good. Saturn's the more challenging one. Let me pause this. Saturn is right here. Notice it is kind of a ruddy or red color. That's partly chromatic aberration from a camera lens. I didn't bother correcting it because I kind of like it. But also it is indicative of the more tan or orange color of Saturn compared to Jupiter, which appears more white when you see him up close. And again, those little white dots next to Jupiter, those are some of his moons. I was able to see both. When will it reappear? Well, the next actual great conjunction, where they're going to be as close as they can get, will be in 20 years, roughly. And it won't be quite as good. They're going to be a little farther apart than they were this time. That's one of the reasons this one got so hyped up. And they're going to be in the early morning sky as opposed to the early evening like this one was. Unfortunately, just like this one, because they will appear close to the sun, they're going to appear low when it's dark out. Only in this case, low in the early morning as opposed to the early evening. Good question. Oh, why did the plane of the moons appear at a different angle of Saturn? So we talked about that during our episode number 8. Planets are crooked. They have different obliquities, and their main moons, their most massive moons, tend to agree with their equatorial plane. So because Jupiter's and Saturn's equators disagree, you're going to see a disagreement in the plane of the moons. So let me briefly bring up a picture just to kind of put too fine a point upon it. So as you can see, Jupiter's obliquity is only 3 degrees, where Saturn's is 27. Also, in addition to the fact that they're differently crooked, so to speak, their orbits are as well. Their orbits do not perfectly agree with each other. This creates differing perspectives when viewed from Earth. Yeah, good question. I love this graphic. Yes. The angles, the tilts, it is handy, yes. I put that together because it's really hard to, find them all in one place. All right, my friends, it's time to talk about the North Star, the subject of tonight's show, and the fact that it's not always the North Star. It's conveniently located above this guy's house. Let me see here. So this cool fellow here. I mentioned that it's ironic that we think he lives in the North Pole because there is actually no ground to stand on up there. So, for example, either Santa Claus takes up shop at the North Magnetic Pole or true North Geographic Pole, but in either case, there is no land to grow, for example, trees on. So he either lives in a submarine or perhaps he's created an artificial island. Maybe it skids along the ice on the giant skis. This is all as realistic as flying reindeer. So, yeah, he lives in either one of these places, and neither of them are a good place to live because there is no ground. So maybe he does that to keep visitors away. But on that subject, this graphic pertains greatly to the topic of our show tonight. There is a lot of disagreement between North Magnetic and North Geographic. Which one matters more to astronomers? Someone tell me. Which of these is more meaningful to astronomers? He could live on the geomagnetic pole. That's true. I guess that would be Canada? Yeah. So he's a little. I'm not sure if that's Greenland or Canada, actually. I should know that. I should know my geography, but he's a citizen of one of those great nations then. So, all right, so let's see. Who wants to tell me? Yes, geographic. So it is geographic north that astronomers worry about because since we live on a moving planet, we have to compensate for those motions when we do complex observations of the universe. And the magnetic pole has no bearing on the motion of the sky because Earth's magnetic field disagrees, as you can see, with the alignment of our rotational axis. Our rotational axis is important to astronomers. The magnetic polarity and its orientation is not, which is good news because, as some of you are probably about to tell me on the chat, if you haven't already, Earth's magnetic field changes position. It actually flips from time to time, and before it flips, it migrates. Currently, the North Magnetic Pole is moving this way. Yeah. So, yeah, you wouldn't want to base anything on the magnetic field of Earth, or you'd have to be constantly adjusting and correcting things. Yeah, now, some of you probably already know it, but the North Star has a lot to do with the North Pole. in that it appears roughly above it. Let's go over some popular mythology about the North Star before we continue. Many people think it doesn't move at all. That's incorrect. In the course of a single night, it does change position. An enormous number of people think the North Star is the brightest star in the sky. It is absolutely not. And I get so mad about that misconception because it is so obviously false. If you've ever actually seen the North Star, you know that it's certainly not the brightest star in the sky. It's not even the 50th brightest star in the sky. The brightest star in the sky is actually Sirius, the dog star, Alpha of Canis Major, and you can see that beautiful bright star this time of year. It's a winter star. You'll see Sirius to the lower right, in the south, by the way, of Orion. So when people say the brightest star is the North Star, I get very angry because I'm like, you have to look south, and right now southeast, to see the, quote, North Star. That should tip you off that something's wrong. Yeah, so the North Star is definitely not the brightest, but it is convenient because it doesn't move very much night to night. And this means people can use it for navigation. Lucky us in the Northern Hemisphere to have a North Star because they don't have one in the Southern Hemisphere. You may have heard of Crux, C-R-U-X, constellation, or the Southern Cross, which is an asterism, not actually a constellation. Crux is not far enough south to actually be the South Star. There is no South Star. Tonight we're going to do something fun. I deliberately did not prepare for this. I'm going to try to simulate a future time period, perhaps, where there might be a South Star. I actually haven't done this before, so I'm kind of curious to see if there is one. I have a feeling there is not going to be a famous named star appearing in the south, near the South Celestial Pole. Okay, before I continue, questions. Clarify the difference between magnetic pole and geomagnetic pole. So if you were to take out a compass, I normally have one handy, I don't have one right now, you would know that it points towards the northern polarity, if you're in the Northern Hemisphere, of Earth's electromagnetic field. You know what? Let me bring up that graphic I like to use during my solar shows. The Earth's magnetic field, although interestingly shaped, does have a dipolar nature, as all magnetic fields do. And so here would be the north magnetic field of Earth, so to speak, and the south. That's where the polarities can be measured as obviously one or the other, if you wish, positive or negative, for example. This has no bearing on Earth's actual tilt. Like I showed you in that graphic with the different obliquities, the rotational axis of a body determines its seasons, like we talked about in the previous show, its physical tilt, because that determines the angle at which sunlight will strike the surface. It affects the way that stars appear to move across the sky as the planet rotates. It's actually a material feature or factor of our planet, and it is also something that doesn't change nearly as quickly as the magnetic fields do. Earth's magnetic fields are the result of a mechanism deep within our planet, the geodynamo, an electromagnetic mechanism where we have molten iron moving around a solid core of iron, creating a natural generator. That process is not forever. Eventually, the molten core of Earth will solidify completely, and the field will collapse, just as it did on planets like Mars. Anyway, the North Star tells you your latitude. It's handy for that, yes. It's not exactly correct, but it's very close. If you measure the apparent altitude, so to speak, of the North Star in the sky, you can figure out what latitude you're at. This is handy if you're setting up telescopes, by the way, because an equatorial telescope mount is designed to compensate for the rotation of Earth. But for it to do that, you have to mechanically align the right ascension axis of that telescope with Earth's axis. And the North Star makes it handy for figuring out what your latitude is and setting the dials appropriately if your mount has a little setting circle to assist you. But you can also do it the old-fashioned way and just point the thing at the North Star, which will get you pretty close. Yeah. Okay, so let's have a little fun. You know, I've already had some good questions. Let's see. Oh, cool. Yeah. What I'm reading. Yep. How is the North Star used for navigation before GPS? Not to sound flippant, but it told you where north was. And that by itself was useful when you were out in the middle of the ocean and lacked landmarks. It's again, very convenient that we have a star that's so close to the North Celestial Pole, and I'm going to define that in a second. But you don't actually need it. Skilled navigators who know their stars didn't need a star to actually be at this foci of rotation, because they would know where a given constellation was supposed to be at a given time of year. This skill was especially very important in the Southern Hemisphere, where you have no South Star, as I mentioned. And so you have to figure out where you are in relation to constellations that will never be at that perfectly non-changing fixed point. Yeah. There are two famous objects in the Southern Hemisphere called the Magellanic Clouds, which often serve as navigation aids. They were used by Magellan for that purpose. Because they appear very low in the sky, it helps you to see where the south celestial pole is. Essentially, you won't see those unless you're in the Southern Hemisphere. If you were trying to go somewhere in the north and you saw those, you'd be in big trouble. You're on the wrong side of the planet. Yeah. So I'm going to put up a simulation of the sky from Goldendale, and we're going to learn a few things about it. All right, so this is the sky right now. I have it on a festive red mode, which is actually not decorational like my tie. It's actually intended to save your night vision. I'm going to turn off that feature. Okay. Now, I'm going to go to now, turn on the planets and the moon and the sun. Okay, this is the sky right now. We're going to go back in time to the year 130 BC, and you'll see why in a second. So let's go to the year negative 100, really? 999? That's amazing. Negative 130 BC. Let's go to the month of March. Let's go to the month of, I don't know, the day of the 20th. Some of you might know the significance of that time of March. That would be the vernal equinox, the March equinox, which signals the start of spring. And back in those days, the ancient Greeks celebrated this time period with a festival known as, a great name, Hysteria or Hilaria, both terms referring to people's moods. It was a time of great celebration because, oh look, our fruits are starting to show up for consumption, and the flowers and the birds and the bees and all that happy stuff. So yeah, it was an old festival, and astronomers of the day, including a famous one, Hipparchus, who I've mentioned in previous shows, made an observation that ended up being quite important. Let me show you. Astronomers were good enough back then at what they did that they could calculate essentially virtual or imaginary positions in the sky, and they could figure out where in the sky, so to speak, the equinox occurred. Same thing with solstices, although with solstices you just use the sun, so it's a little bit different. Speaking of the sun, let me turn on the atmosphere here. I'm going to turn on the meridian. Okay, it is now solar noon, or close to it. I'm going to zoom in a bit here. I'm going to turn off the atmosphere. I'm going to turn on constellations. Go back in time a few hours. Let's see, actually, let's go back in time a few days. Long story short, it was noticed that the sun was in the constellation of Aries around this time. If I go back to the exact day, I'm actually cheating a little bit just so I can show you. This was specifically mentioned when the sun was right about here. This ended up being called the first point of Aries. And the first point of Aries was essentially a 0 point in the future charting of the sky. And astronomers of those days, believe it or not, were so good at what they did that they noticed that something was happening. They noticed that something was changing. I'm going to zoom in a little bit here, zoom in on the sun a bit. I'm going to go into the future in increments of years. And I want you to notice something. Keep watching the screen. Actually, let me zoom in a little more so it's even more obvious. Actually, I can do that too. That's actually good. As I go forward in time, now it's the year 80 BC, now it's the year 70 BC. First of all, you might notice the sun seems to jerk back. Watch. 1, 2, 3, 4, back. 1, 2, 3, 4, back. The reason that's happening is because of something modern known as leap year. Some of you have probably heard of that before. If you're not aware of the fact, leap year attempts to reconcile the Gregorian calendar with the actual astronomical motion of bodies. And when you chart, for example, the appearance of the sun at, in this case, let's use the solstice, summer solstice, you'll see that it seems to shift ever so slightly every year and then jerk back because of leap year. Leap year is, of course, applied because a day is not actually 24 hours, a year is not actually 364 days. And so every now and then we have to essentially add a day, and of course you know what that is, leap day. It's February, 29th, every few years. You might notice that there is not consistency here in how we apply the leap years. You see how there's like these gaps in this unusually long track. That's because the rules for applying leap year are complicated and occasionally arbitrary. There is a mathematical algorithm that needs to be applied and has not always been applied with consistency, thank you, throughout history. And so you get this not exactly reliable offsetting of astronomical object positions, because we're literally changing the definition of time every few years to fix the problematic Gregorian calendar. Anyway, so I'm going to turn this off. Go back to my simulation here. I'm going to keep going back and forward in time. I'm actually going to go forward, and I want you to watch something. Ignore the jerking motion caused by leap year. You might notice the sun seems to be gradually migrating to the right. What's actually happening is the entire sky is moving to the left. This phenomenon became known as the precession of the equinox. The reason we say precession is because precession indicates backwards motion, where procession indicates forward motion. So ancient people observed the precession of the equinox and discovered that notable events like solstices and equinoxes ended up drifting through the sky over time into various zodiacal signs. You know, the signs of the zodiac are projected onto the celestial sphere. Essentially, they are on the ecliptic plane. And the plane of the ecliptic actually carves out the path of the sun. So they notice the sun appeared to be wandering through the different constellations throughout the course of time. This shows you how good of records they kept, because the fact that ancient astronomers, without the aid of optical magnification, could determine this shifting over time is very impressive. It demonstrates they were extremely observant and that they took this stuff very seriously. Of course, they didn't fully understand why it was happening. It turns out that Earth's axial tilt precesses the entire tilt, the entire axial motion of our planet, carves out a cone-shaped slice of the sky. And where these different famous calendar events like equinoxes and solstices tends to change, tends to go backwards. So I'm going to show you a video that helps kind of hopefully helps us understand this. So here's our Earth. We're going to show it in three-dimensional space. You can see the equatorial plane, which, actually, let me pause it so we understand. The green equatorial plane is a projection of our actual equator into the sky. It's essentially a projection of what becomes the celestial equator. The equatorial plane, let me go back. This is the plane of our orbit. So watch what happens over time. You'll notice that the axis precesses. Now, it's important to understand this does not happen quickly. I've noticed a misunderstanding about this mechanism. Hold that thought. I want to show you something. I'm going to go back to, oh, by the way, there it is showing at the ecliptic plane. Let me show you something really quick from a few weeks ago. We talked about the position of the plane. Oh, sorry guys, thanks for waiting. So here's an image of the Earth, and it demonstrates a 23.5-degree tilt. Here's another image of it. It's important to understand that the tilt in relation to the sun does not change in the course of the year as the Earth orbits it. So we're not talking about a wobbling top phenomenon that applies to the course of a single year. In fact, this takes thousands of years to play out. So don't confuse those mechanisms. Earth is on one side of the sun or the other, but the 23.5-degree tilt remains orientated, so to speak, a certain way. So, as I was saying, notice we have a little Aries symbol here. Oh, and there we go, starting with Aries. We go back to, actually, let's go back to that. The reason it says Aries is because this is when we first noticed it. So, This symbol indicates that first point of Aries I talked about earlier, and it also essentially impacts, or rather denotes, the position of the vernal, or let's say March equinox in the sky. And of course, as you can see in the year 1000 BC, it was in Aries, and it seems to move. So imagine this. As the precession causes the first point of Aries, which we still call the first point of Aries, by the way, even though it is no longer in Aries, as it causes that imaginary point to move to the west, so to speak, the stars appear to move to the east. And again, this is where the precession comes from. Notice, oh, look at that. Remember the famous song, The Age of Aquarius? It talks about the fact that the first point of Aries will reside in Aquarius. Technically, it doesn't know. It's technically still in Pisces, based on modern mapping of the sky. There you can see the first point of Aries moving around. Also notice the large number of years involved in this process. Precession is not quick. I'm going to keep watching this. Maybe you can add up the amount of years in play here. We're now to the year 14,000. We're now to the year 16,000. 18,000. You might remember we started in the year 1000. I'm going to talk about that in a second. Back to Aries. So 22,000 years plus the 1 for 1000 BC. And Aries has a bit of size to it, so it actually spent some time in Aries before 1000 BC. And what we discover is this rotation, this process, requires about 26,000 years to play out. Now, it's actually very specific, 25,772 years, but it's not actually worthwhile to memorize that number because the value changes. We're going to talk about why it changes in a few minutes, but just be aware that you can just say 26,000 years and you wouldn't be wrong. Notice that as we watched the precession of the first point of Aries moving along the ecliptic plane across the zodiac, we also drew a circle in the sky above the Earth and another circle in the sky below the Earth. Interesting. You probably know where I'm going with this. Occasionally, a conveniently bright star will appear on or near this circular track. Let's talk about that. So we're going to draw it. Now, I want to tell you what NCP stands for. NCP stands for North Celestial Pole. So the apex, the highest point of the celestial sphere, as according to the equatorial grid system that's based on Earth itself. Notice that in the year 2000 BC, it was over here in the constellation of Draco, the dragon. Now, I see a very famous star. I'm going to pause it again. In 2000 AD and thereabouts, we have the famous star Polaris. This is the star Polaris, which is the tip of the handle of the Little Dipper asterism. And that's why we have a North Star at this time, because that star happens to be close, not exactly on it, looks on it, but we'll talk about that, close to the North Celestial Pole. Let's let this keep going. Someone's mentioning some famous star names. That's good. Hold that thought. I'm going to show you in a second. There's a number of famous stars here. Some of them are closer than others to the North Celestial Pole. And we're back. Now, I saw someone in the chat listing famous stars. Let me show you a chart that might help you appreciate that. Just one second. So here they are. Someone mentioned Thuban in the year 3000 BC. That's a famous star. And it's often associated with the ancient Egyptians. Although ancient Egyptian society persisted for so many thousands of years, that Thuban was not always their North Star. This is rather impressive when you consider the precision at which they built the pyramids. They actually aligned them to north, including during times where there was no convenient North Star. So it shows you that the ancient Egyptians took their astronomy very seriously because, like I mentioned earlier, you don't actually need the convenience of a pole star to determine the poles. You just need to pay attention to the motion of the constellations throughout the year. So well done. There's our famous North Star now, Polaris, 2000 AD. Alderamin, 7500 AD. Now, this is the one I always like to talk about. Vega. As you can see, Vega will not be directly within the North Celestial Pole, but it is close enough. And Vega is a very bright star. It's one of the brightest stars. So, in the year 14,000, indeed, we will have a bright North Star, much brighter than the current North Star. Don't wait for it. It's not worth it. You know why? Because you don't need these things to navigate anymore because of our modern understanding of the motion of things and also our gizmos and gadgets. Like GPS, which someone mentioned. Some have argued that it's a bad thing that we're becoming so dependent on technology for navigation. We should probably have not lost some of these skills. People often bring up the Boy Scouts and the Girl Scouts. They still teach these things. I also heard recently that the U.S. Navy has reinstituted training on celestial navigation. That's cool. Again, it's very important to people at sea because you lack the convenience of landmarks. But if you know your stars and you have a few instruments to help you measure their positions with accuracy, you can figure out where you are just by figuring out where they appear to be and knowing exactly what time it is. And then, oh, here we have another star, Tau Hercules, another star in Hercules. Again, this takes about 26,000 years to play out. Now, I saw the chat moving a bit while I was talking, so I'm going to read some chat. Ponder these things. I'm going to show you some more animations in a bit. And we're going to talk about why this happens. We're going to talk about why Earth's axis precesses in this way. All right, so I think you might have the month of April, not March. I'm not sure how that maybe that applied to the simulation. It works either way, though. Let's see. Yep. Okay. I see some responses that are not questions. Thanks for the support, my friends. All right, so we're going to continue, and we're going to have a bit of fun. We're going to demonstrate this process in simulation. All right, let's go back to now. Let's go to March. This is next year. I think it was the 21st, is it? Yeah. So now we're to the vernal equinox for next year. And notice something. The sun is inside Pisces. So like I said, we're not actually in the age of Aquarius. We are technically in the, if you believe in such things, in the age of Pisces. It'll take a few more centuries before the sun actually passes into Aquarius. This is Aquarius right here. The water bearer, yep. And up there we have Pisces, the two fish, yes. So as you can see, the sun is in Pisces during the next vernal equinox. Just for funsies, you want to see how long it'll take? I'm kind of curious. Let's go into the future a whole bunch. I went backwards. There we go. That's what it'll look like in a few centuries. Okay, now, I told you that I would show you the North Star, and I'm going to simulate a few things. I'm going to turn on the equatorial grid. The equatorial grid is based on Earth itself. I'm going to turn on the celestial equator. I'm going to turn off that grid for a second. Notice this blue line. That blue line is the celestial equator, so in other words, a projection of our equator into the cosmos. And this is the equatorial grid, which is based on it. Again, that word equatorial might indicate something. Now, let's find the North Celestial Pole. To do that, we're going to go north. And we can clearly see a famous star there. But notice it's not exactly there, as we talked about. Polaris is right there. And this is the North Celestial Pole. As you can see, there is actually no star, or no bright star anyway, right there. But we are relatively close to it. Close enough, so to speak. Let's speed up time. And you can see Polaris dancing about the North Celestial Pole. Now, the reason you don't notice this dance so much in real life is because this simulation right now is a very magnified view. We've essentially virtually zoomed in. In a telescope, you would notice this motion very starkly. But if I zoom out a bit, simulate normal human vision, as you can see, Polaris doesn't seem to move very much. Because, again, it's not that far from the North Celestial Pole. So now let's go to some of those times that we listed. Let's go back in time. What year was that? Let's see. To the year 3000 BC, and we're going to look for that famous star I mentioned. Time machine active, watching the clock. It is now the year 1000. It is now the year 0. It is now the year 1000 BC. It is now the year 2000 BC. And here we are at 3000 BC, or close enough. Oh, look at that. Just as indicated in that graphic, we have the star Thuban. So Thuban would have been the North Star back then in the year 3000 BC, just as indicated in our educational slide. Now, let's have some fun. Let's go to the year 7500 AD. I'm going to go even faster this time. We're in the year 4000, nothing to see. It is now the year 5000. It is now the year 6000. It is now the year 7000. Oh, here we are, 7500, close enough. I don't see that star, although I see it may have a different name. Let's see. Alderman. Let's go into the future even more. I bet you it's farther away. There it is, right there. So as you can see, Alderman will not be as high of a quality North Star as Polaris is, because Alderman appears farther from the North Celestial Pole. Now let's go to the year 14,000. And this is the one I mentioned that was kind of famous. 10,000, 11,000, 12,000, 13.5, almost there. 13,700, let's go faster. All right, the year 14,000, give or take. As you can see, Vega is also not that close. It's farther from the North Celestial Pole than Alderman was. So even a worse North Star in terms of alignment with the North Celestial Pole. However, it is very bright. So you'd have no trouble pointing it out to someone. So someone would say, where's the North Star? And they'd say, oh, right there. And they'd point in the north, and you probably would immediately go to that star because it is one of the brightest stars in the sky. Yeah, so although Vega will not be as close to the North Celestial Pole as Polaris, it may be even more handy in that it is brighter. However, by the year 14,000, who knows what we will be up to? We may not be even recognizable anymore. We may have augmented ourselves with virtual technology. Maybe we'll be cyborgs, or maybe we'll be living in tanks, or our brains connected to computer networks or something. Maybe we won't care about navigation anymore. Maybe we won't go around everywhere. Maybe we won't fly or drive or take boats or trains anymore. Who knows? But if we do end up needing to navigate via the stars, we'll have this convenient waypoint. Questions about that? Would there ever not be a North Star? Yes, all the time. Yes, that's right. The famous double-double is a wonderful actual double binary system, so a quaternary system. That's a summertime star. Since you brought it up, there it is. Let's have a little tangent just for funsies. So this is the double-double. This is actually an object we like to show visitors during our shows in the summertime. So if you zoom in close, you'll see a star. Let's pick on this one here. This is double-double 1. Oh, look at that. Oh, still just 1. There's the other one. And then we have another pair over here. So 2 pairs of binary star systems, and they're actually orbiting each other in a dumbbell orbit. So that was a fun little summertime tangent. Now, as far as someone asking, would there ever not be a North Star? Yes, as I was saying, all the time. So, for example, if you wanted to split hairs and be really specific about what you define as a North Star, then right now, when Vega is the North Star, so to speak, it's really not, because it's pretty far from the North Celestial Pole. In fact, it's far enough that even without magnification, you can see that it makes a little loop every night. Watch. So this is a course of a single day. As you can see, Vega definitely does dance. And again, this is right now simulating a view closer to what a person would see without using binoculars or a telescope. So you could argue that Vega is technically not the North Star right there. However, let's go back to one of those random times. Let's just type it in directly. Let's go to the year, I don't know, 0. It is now the year 0. Looks like Kochab will be a decent North Star. That's not a terribly bright star. But still not exactly there. And as I already pointed out earlier, also, if you do get really specific about what a North Star should be, you end up realizing that there never is a North Star, that there never is one, if you want it to be precisely above, so to speak, Earth's true North Pole. Questions about that? We're back to now. Let's see. Would space travelers need a North Star? That's an interesting question. So when it comes to spacecraft currently, a lot of people don't know. This is actually quite cool. Modern spacecraft being built right now always have some sort of low-resolution camera that is intended for wayfinding. It allows astronomers back on Earth and scientists to figure out the orientation of the spacecraft. So, for example, if Vega is actually one of those guide stars, or Deneb is another famous guide star, if the guide star is not where it should be on the sensor of the guide camera, then astronomers know that the orientation of the spacecraft is off. Very handy, because in the case of spacecraft, they're moving so quickly through the solar system that the planets won't be where they should be when it comes to Earth's perspective. So you can't navigate by the positions of the planets. But stars are so far away that the few thousand miles per hour of a space probe will not cause them to dramatically shift in position so much that you couldn't use the stars for navigation. It's been kind of entertaining in the past to see footage, so to speak, from the navigation camera of spacecraft, because it allows you to essentially to see their course. It's kind of neat. I don't have one of those videos handy, but I have seen navigation footage from the Voyagers. I've also seen it from the New Horizons spacecraft. And it's neat to watch the star field staying mostly steady, but sometimes it'll kind of jerk around like that, and that's where they're making adjustments to stay on course. Or deliberately changing the orientation of the spacecraft to use a different instrument or to align its transmitter or receiver with Earth. Yeah, so yes, you do need to use a navigation camera using stars as your landmark, so to speak, in outer space. There is, by the way, an interesting idea there. We're talking about, and this is currently in the works, multiple world governments essentially creating a form of GPS for outer space. So there'll be satellites whose job it is to provide positioning data, not just for objects on the Earth's surface, but objects anywhere in the solar system. It's a cool idea. And it would dramatically increase the motion resolution, the positioning resolution of spacecraft. This is going to become more important over time because we're starting to do some things in space that require incredibly precise placement of objects. For example, we're talking about putting a gravity wave observatory in space, where you'd have spacecraft separated by literally millions of miles, shooting laser beams at each other. This allows you to create an incredibly sensitive gravity wave observatory for detecting, for example, black hole collisions and neutron star collisions. So you have to know precisely where those machines are if that concept is to function properly. So yeah, the position of things in space, although we can use stars currently and do, we're talking about improving our ability to navigate in space using artificial means, just like we have on Earth. So that's a good question. All right, so I like that. Now, I told you I was going to go to the south, and we're going to do something else. Watch this. Now we're going to go to the south celestial pole. Oh, wait, before I do that, check it out. I'm going to turn on the images here. Notice there are two blobs. That is the Large Magellanic Cloud, the LMC, and over here, this is the Small Magellanic Cloud, the SMC. And they are dwarf galaxies of irregular structure. They're not high in stellar population. They have hundreds of thousands of stars, possibly millions of stars, and they're very close to us. They are less than 170,000, not million, 170,000 light years from us. We now know that by measuring their motion, that they are essentially attendants of the Milky Way. They are essentially companion galaxies to our own Milky Way galaxy. You cannot see these in the Northern Hemisphere. You have to go to the Southern Hemisphere to see them. They are handy navigation aids, and as I said, Magellan used them. That's why we named him after him, because as you can see, they're not terribly far removed from the South Celestial Pole. So that's something to keep in mind. Those of you who have ever been to the Southern Hemisphere may have seen them. Let's see if anyone in the chat has. Tell me in the chat if you have actually been to the Southern Hemisphere and have seen the large and the small Magellanic Clouds. I'm going to wait for a second. While you do that, I'm going to look for a picture. I might have one. Let's see. No, thought I did. Darn. They're very pretty. I've never actually seen them myself. I've never been to the Southern Hemisphere. Someday I will, and I plan to take pictures of those clouds. So back on track. I'm going to zoom in here. As you can see, there are definitely no bright stars here. Now you might say, well, Troy, what about these stars? Those are south stars, aren't they? Well, the thing is, they're just so dim. The software is allowing you to see them as brighter because we've zoomed in, essentially simulating the effect of a magnifying optic with larger glass than your eyeball. But if you were to zoom out, these stars essentially disappear. You would not be able to make them out very clearly, and they would certainly not stand out as navigation aids. So there currently is no south star. What would you see if you lived at the equator? If you lived at the equator, you could actually see everything, but you'd have to wait until certain times of year. Because, for example, where we live, there are certain constellations that are what we call circumpolar. Same thing for people living, let's say, for example, in Australia, someone living in Australia, there are certain constellations that never set. But if you do live on the equator, then essentially all of the constellations set. And so you'd have to wait for, like I said, a certain time in the year to see a given constellation if you live in the equator. But the cool thing about the equator is you can see everything, or most everything. Let me just let me put too fine a point on that, because that's actually an interesting topic. I'm going to point to the north. We're back in the northern hemisphere right now. The green line is the horizon. So if something goes beneath that line, then it has set and you won't see it. But watch. Notice that everything in this circle, let me zoom out a little more, everything within the circle that I'm drawing with my mouse never sets. And so that would be considered circumpolar. That is an effect of where we live, our latitude here at Goldendale, 45 or 46 degrees. If you're closer to the pole, you'd have more circumpolar things. If you're farther from the pole, you have less circumpolar things. There are some very famous things that are circumpolar indeed. For example, let me show you. Let's get the artwork on here. Cepheus the king, Cassiopeia the queen, the terrible constellation Camelopardalis the giraffe, which is extremely dim and definitely does not look like a giraffe. Parts of Lynx, of course, Ursa Major, the Big Bear, and the very famous Big Dipper. Draco the dragon. Oh, and of course the Little Dipper, which is an asterism within Ursa Minor, the Little Bear. These things never set. Different constellations, again, would be circumpolar or not, depending on where you live. I'm going to pause it because I discovered something for fun here. Check it out. Capella here. I noticed this by accident after I moved to where I live now. Capella is the brightest star that doesn't set where we're living here. As you can see, Capella almost sets, but not quite. It is the alpha star of Auriga, the charioteer. So even though most of the constellation sets, its alpha star does not. If we were just a few hundred miles south from here, if Goldendale Observatory were just a few hundred miles south, Capella would set. That being said, all this is true based on a perfectly unobstructed horizon. If you're lucky enough to live in a place where you don't have, for example, hills and trees and other obstructions, maybe buildings if you live in a city. So this is simulating a horizon with no objects blocking your view. As a result, many people would see, for example, Capella setting because it goes behind the trees. That happens here. I was only able to figure this out from the roof of the place and realized, wow, that doesn't actually set. Look at that. Neat. So let's go to the southern sky again, like I said we were going to. Turn off the artwork here. Now, let's go into the future, and I'm going to watch for bright stars. The other problem is there aren't that many bright stars in that part of the sky anyway. That's another issue. I'm watching for labels to appear. Let's go back to the year 0. Okay, this is the year 0. There is no south star. This star is interesting. That's actually not a star. That's a globular star cluster. Which one is that? Oh yeah, 47 Tucanus. I should have known that. So that's kind of cool. So you can actually see that as a little smudge. You don't need a telescope to see that. That is a globular star cluster. That's kind of cool. So that would be an interesting navigation aid. It's not, again, exactly in the south, although it's similar in distance from the south celestial pole to the Small Magellanic Cloud. So that would have still been a pretty handy navigation aid. All right, so let's go into the future a whole bunch. I'm watching for something bright to get close, and I'm not seeing anything. No, I just don't. Nope. Nope. It is now the year 345. So, let's go faster. Oh, I thought I saw one. Let's go back. What is the year now? 14,000? I bet you I'm going to fail at this. Let's see. Okay, so this star, 71 Puppis, is kind of bright. So in the year 12,521, you could use the star 71 Puppis as a relatively, let's say, acceptable guide star for a southern guide star. But again, don't wait for that. That's 10,000 years from now, isn't it? Wow. So, sorry, Southern Hemisphere. You guys don't have the convenience of a bright guide star the way we do here in the north. Questions about that? Let's see. How do they point to South Pole of the Southern Cross? Okay, Southern Cross, that's an asterism. It's a part of Crooks. Let's go find it. So this is Crooks. Let me turn off the grid so you can see the lines. So Gacrooks and Alpha Crooks, also known as Acrooks, form a line which you can kind of follow to the north, rather south celestial pole. It's not exact. Let me see if I can make it for you. I'm going to draw it. So I'm going to draw a line. Here we go. We miss, but we don't miss by a lot. This is very similar to the way you find the North Star by following the end of the cup of the Big Dipper, where you can follow those stars up or down depending on where it is in the sky at a given time of year, and it gets you close. In this case, this is what you're talking about. People will use crooks to draw a line between these two stars and follow along that vector. And again, we miss, but it doesn't miss by a huge amount. The problem is, though, in the south, where it becomes less convenient than with what we have in the case of Polaris and the Big Dipper pointing towards it with the cup, is that you don't know where to stop necessarily, because I could just keep going and zoom right past the South Celestial Pole because I didn't know where to stop. Because, again, you don't have the convenience of a bright star. So that does help, but it's not a perfect solution. Now, on this subject, companies know this when they sell telescopes, that it's inconvenient for people living in the Southern Hemisphere attempting to align an equatorial mount. And so sometimes they'll actually have what's called a polar scope, which is a sort of finder that is a very wide field of view, and it has little plastic or painted dots that indicate the positions of famous constellations near the South Celestial Pole. And you'll spin this thing around to match a given time of year, and you'll look through it and you'll say, okay, this is kind of lined up. And that's how you find the South Celestial Pole conveniently using this tool. So that is essentially an accessory that comes with many telescope mounts, especially ones sold in the Southern Hemisphere. I have to say, we do take this for granted here in the north, having a relatively bright North Star. It is convenient and something that is not shared by our friends in the south. Yeah. That was a good question. Okay. Questions. Now, as we get close to the end of the show, I want to talk about why all this motion happens. The camel leopard, that's funny. Yeah, I love that term for a giraffe, the camel leopard. So, in space, things only tend to change course, so to speak, or alter their orientation in some way if they're acted upon by a force. Unlike on a planetary surface where you have, for example, air or water that creates drag on a thing and causes it maybe to shift position or slow down or whatever. In space, you lack a fluid medium to create drag. And so you would think that an object would remain on course, so to speak, forever. But of course, there are other forces at work besides just the friction, the electromagnetic interaction of friction. Of course, there's also gravity. Gravity tugs on things. We live on a planet. that is tugged on by Earth's moon, in our case. It is, of course, also tugged on by the sun, and Earth is also tugged on by the other planets. I showed you guys a video a few weeks ago. Let me slow that down. Of the lumpy Earth. This three-dimensional model illustrates the fact that Earth's mass is distributed asymmetrically. We have a lumpy planet. This globe does not just illustrate actual altitude variation. It's demonstrating mass concentration. So because mass on our planet is not uniformly distributed, our planet is not uniformly affected by the gravitational influence of other bodies. So for example, let me pause it on some random spot. The moon will pull more on the Himalayas than it will, I don't know, the middle of the ocean over here. That's interesting because that creates some shift, that creates some variation, that creates a little bit of chaos. Because we live in the amazing future that we live in, we are able to take measurements precise enough and plug them into computers powerful enough to actually become aware of some of these deflections. And we've discovered that some of the deflections are unique and different from the overall average deflection. So we talked about the fact that the equinox precesses, that's the precession of the equinox. Now we can say a better, more modern term is axial precession. And that's averaged out over thousands of years, like I said, about 26,000. But then there are much smaller motions, like one referred to as nutation. Nutation causes precession as well, although to a much smaller degree. And it's on about an 18-year cycle. We can actually measure nutation. It's only a few arc seconds across in terms of deflection, so it's incredibly slight. And by the way, if you're not sure what an arc second is, I've used that term a few times before. An arc second is an extremely tiny distance measurement in the case of diameter in space, the apparent diameter of objects. To give you some idea of how small an arc second is, there's about 1,900 arc seconds in a half a degree, which is about the width, so to speak, of the moon. So we're talking about just 6 or 7 or 8 arc seconds of deviation over this 18-year period. That's nutation. And that's not something you'd ever notice, but astronomers can, using very high precision measurements of the positions of things in the sky. So that's interesting. And then there's something else. There's a shift caused by Earth's crust itself moving on a molten mantle. Now I use air quotes when I say molten because we often think of the mantle of the Earth or the stuff beneath our feet as fluid or liquid. Even though it's technically molten, if you were to interact with the mantle, you'd discover that it's essentially rock. You wouldn't be able to like stick your finger in. Let's say you had a glove that allowed you to handle the temperature. You wouldn't be able to shove your finger into it. It would feel like solid rock. The only reason why the mantle seems fluid is because the crust is so incredibly heavy. The crust can move on top of the mantle. It moves because of events like volcanism. It moves because of events like earthquakes. And then even very small things like tides cause Earth's crust to shimmy very slightly. And again, astronomers have gotten so good at charting the positions of things that we can reveal this very slight deviation caused by the crust itself, which we of course live on, moving around. So you have the least severe motion, which is this polar shift caused by crust itself moving. You have the more severe motion of nutation, which takes about 18 years to play out. And then we have the obvious very large scale motion, the axial precession, which takes, as we said, about 26,000 years to play out. Now, it's not just Earth's lumpiness that causes these interactions. It's also the fact that Earth is not a perfect sphere in terms of mass distribution along its equator. Earth is fatter around the middle than up and down. Our planet is not a sphere. It's an oblate spheroid. So oblate, in this case, meaning its fatness. Earth is thicker around the middle than it is on the top because of that very important and very famous centrifugal pseudo-force. Centrifugal force, which is really just a manifestation of inertia, causes rotating bodies to want to flatten out into a disk. Of course, if the material is strong enough not to do that, it still might be just weak enough to bulge a bit. So because Earth has an equatorial bulge, that means the stuff, objects, let's say the moon or the sun, will tug down at one time or down in a different way, depending on our orientation related to those objects. So yeah, the bulge of our planet is also acted upon by gravity bodies in our solar system. Questions about that? is if the magnetic pole flipped tonight, how will the flipping of the magnetic pole affect current navigation tools? So the good news is that we don't need magnetic navigation anymore because we've gotten better at measuring other things. In the case of everyday life on Earth, really no one who's serious about navigation, for example, aircraft, pilots, airlines in general, shipping industry, giant ships at sea, they're not using compasses anymore. Compasses are useful for determining your heading, but they're not required because we can infer position and vector via more advanced means. So yeah, if Earth's magnetic field flipped tonight or suddenly moved very, very much, it wouldn't be an end to navigation. In fact, I had to say, myself included, I don't know many people who use compasses at all anymore. Compasses can be used in our technology to help calibrate them. For example, your phone has an internal compass, which helps increase its wayfinding accuracy by getting it in the ballpark before it relies on satellites, for example. Telescopes, we mentioned earlier, telescope mounts will often have a magnetic sensor, a magnetometer, which again allows it to find the rough north. It won't be good enough. By the way, this is something we're going to talk about next week. Even if you can measure the magnetic field of Earth, even if you can figure out where the North Pole is, the magnetic pole, that doesn't help you find out where the North Pole is unless you know where you physically are, because depending on where you are in the world, the magnetic deflection or deviation will be different. Here in Goldendale, it's actually quite strong. It's like 16 degrees, so your compass is wrong by 16 degrees. But if you were in different places, I think like Ohio I figured out once, or maybe it was Missouri, your compass, by coincidence, is pretty accurate because of where you're standing in relation to the true North Pole and the magnetic north. So yeah, it would not be some world-ending crisis if the magnetic field suddenly flipped. Oh, and by the way, that applies to a lot of things. Doomsday fans love to talk about the magnetic pole, the magnetic field of Earth flipping. It will do it. It will not destroy our planet. Please don't worry about that. Yeah. All right, so questions. Does climate change have an impact? Yes, because it causes accelerated ice melting. Remember we were joking earlier about Santa Claus living on ice floes. It's kind of alarming. The ice sheets at the North Pole are thinning and thinning and thinning. And that actually, although very minorly, does affect the mass distribution of our planet and would definitely affect what we talked about earlier, that shifting of the crust. Yeah. I wouldn't, of all the things to worry about, though, I wouldn't list that as the primary concern when it comes to climate change, because it's such an incredibly minor impact when it comes to the precession of Earth's axis. Yeah. Good question. We're pretty much done, and actually we did it on time. It's 8:02. I'm going to take a few more minutes to take questions. Wow, my brain tonight. I'm going to answer questions if you have any, and then we'll be signing off. So feel free to ask some questions. How did Pangea affect the magnetic pole? Well, when we had the one supercontinent, I don't know how it would affect the magnetic pole. Don't forget, Earth's magnetic field is not a product of surface mass or iron distribution. That's something that our grandparents were taught, that Earth must have these huge concentrations of iron near the poles, and that must be why we have a dipolar field. Now we know better. It's that electromagnetic mechanism I talked about earlier, the geodynamo. So the surface conditions really wouldn't affect the overall magnetic field of Earth very strongly. However, this is interesting. Rocks, which contain metallic elements, can remember, so to speak, the orientation of Earth's magnetic field because they become lightly magnetized. And that's actually one thing that geologists do to figure out where a rock or a given formation of rocks was at a given time in history, or how much it's moved, or how it changed its orientation, by mapping its weak residual magnetic polarity and comparing it to the modern magnetic field. That's one of the ways we discovered that Earth's magnetic field does flip in a somewhat cyclical manner, and then it takes thousands of years to happen. Interesting. This is not only unique to Earth. We can do the same thing on other planets. For example, Mars, I mentioned in another show, has a weak magnetic field that is mostly residual magnetism trapped in the material near its surface, essentially stored, if you will, from the time when the planet had a stronger overall magnetic field. That's a good question. So someone asked, why does compass north declination change over years' time? Earth's magnetic field wanders, and I'm going to save that for next week because we're going to talk a lot about that in length. You're probably going to learn more than you want to know about that topic. And again, it has to do with that geodynamo mechanism we were just talking about. So yeah, hold that curiosity for next week. All right, I'm looking for any bonus materials I might have forgot to share with you. I'm going to put this decorative video back on the screen from the 22nd. Oh, look, it's still in slow motion. Let me speed it up. Oh, you know what I forgot to show you? This is from the 17th. We had a very pretty lunar conjunction with the planets Jupiter and Saturn on the 16th. We missed it, but on the 17th it was still kind of cool, so check it out. So you can see the beautiful crescent moon there, and then we see the great conjunction of Jupiter and Saturn, almost great conjunction. And as you can see, they are setting. The telescope is tracking them, so the ground seems to be rising up. Yeah. All right, let's see. So as the solar system, this is a wonderful question. As the solar system is moving around the galaxy center, does it not change the orientation and rotation of Earth? Not really. We essentially live in the domain of the sun. The sun is like it creates this sort of environment, and we refer to it as the heliosphere. The heliosphere is the domain of the sun, which is mainly its electromagnetic domain. But deep within the heliosphere, the planets and the comets and the asteroids, they are dramatically affected by the sun's gravity. So we essentially go along for the ride. The sun orbits the core region of the Milky Way galaxy, and we go along with it. The sun is affected. Its trajectory and speed is affected by other stars in the Milky Way, by density clusters, density or high density enhancements in the core region. As we move around the core, indeed, the sun's orbit does change ever so slightly. But again, we go along for the ride. So Earth's orbit will not be dramatically affected, but the orbit of the sun will be. So we would be very, very indirectly affected by that. So on that thought, last week we did a show about things being crooked, and I had a graphic that showed you a few different spheres and planes, and notice how nothing agrees. So we have the north ecliptic pole, which is essentially the pole, if you want to call it that, the above and below of the ecliptic plane, which is really just a projection of Earth's orbit around the sun. Then we have the north celestial pole, and over here the south celestial pole, which is of course based on Earth's obliquity, the tilt of our planet. By the way, this is why we say the Earth is 23.5 degrees tilted, because of this discrepancy between these two metrics. And then notice, if you want to, let's say, extrapolate the ecliptic plane as the plane of our solar system, which is not totally incorrect, because the other planets also roughly agree with it, you'll notice the north galactic pole disagrees strongly with the ecliptic plane. So, we live on a crooked planet in a crooked solar system. Every star system has a different orientation. There is no up or down in space, unless you define that by motion vector. So you could argue that we're going in given direction, so up or down, away from that will probably be quite similar to other star systems, because most of the stars in our galaxy are moving in a prograde manner. Essentially, they're going in the same direction around the core region. Not all, but most. So if you wanted to get real complicated, you could create another charting system, and of course we've done this, a grid system based on our motion. But as far as our motion through the galaxy. But as far as what we experience on Earth and what we measure, we see crooked upon crooked upon crooked. And this is what makes astronomy so difficult, because all the motions that we perceive are baffling, especially to our ancestors who didn't understand that everything was crooked. They dogmatically assumed that everything was perfectly centered, that everything was perfectly coaxial, that everything was perfectly lined and planar, and that everything was doing what you expected something to do. And so when they saw the motions of things defying that expectation, they became baffled, and they came up with all sorts of explanations, some of them decent, some of them terrible. You may have heard of the epicycle theory, the idea that planets are actually doing these little loop-de-loops around the sun, around the Earth, of course, because people who believe in epicycles also think that the objects, including the sun, are orbiting our planet, which of course they're not. But that was an attempted explanation for the chaos we observed in the universe, because again, crooked on crooked on crooked. Good question. That was a good question. Let's do one more minute. And everything was crookedly orbiting the Earth. Yeah, that's right, exactly, yep. Yeah, okay. So, did we learn anything? Hope so. Yeah, I actually am happy we pretty much ended up on time, and we had some time for questions. Let's do one more question, and I'm going to sign off. I will encourage at this time questions about the Great Conjunction again. If you haven't seen it yet, be aware it's going to get more difficult because the pair are appearing lower and lower every night. Let me show you. So let's go to a few hours ago. This is back in, this is, let's go to, this is now. Okay, so we're going to go back in time a few hours. Let's turn on the atmosphere and the fake ground. Let's back up time a little bit. As you can see, they're quite low after sunset. Let's go into the future one day. Lower, 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 which means you'll have to look earlier, which is hard because, as you can see, the sky is brighter. They're going to be harder to find. So I encourage you to go out as soon as you can to try to see Jupiter and Saturn. If you don't know where to look, look to the low southwest. And if you don't know where south is, I don't know. I encourage you to learn your directions. If you have a landmark near you, you could use it. For example, here in Goldendale, we are directly north of the river. So if I see the Columbia River, I know I'm looking south. And if I look away from that, I'm looking north. Yeah. Now, if I'm facing south, then if I look to my right, I'm looking west. And if I'm facing south and I look to my left, I'm looking east. So there you go, left and right. I know that's very challenging. Okay, so I don't think I got a final question. No one? You got, I'm going to give you 30 seconds. Come on. And this will be your last chance. 30 seconds for a question. Let's see. By the way, thank you to my moderators tonight. They've been doing a wonderful job of filtering the chat, which allows us to move quickly through the questions, and we have had them. What is the reference for the star positions and velocities in Stellarium? That is a fantastic question. And the great thing about Stellarium is it includes a lot of different measurement metrics, a lot of different standards, a lot of different reference frames. So, check it out. If I pick on a star, let's say Markab here, you'll see a bunch of things appear on the upper left. These are all different coordinate systems based on different frames of reference. So, let me read them to you. Right ascension declination based on J2000 is the position of things according to star charts that were drawn in the year 2000. We redraw star charts every 50 years, so the next star chart epoch will be 2050. But then right below it, we see right ascension declination on date, and notice the numbers are different. That's because everything's shifting and moving, as we talked about tonight, and because of that, star charts are technically incorrect. In both cases, these coordinate systems are based on Earth, on the equatorial grid. So essentially based on Earth's equator. Next, we have, I'm going to skip HA deck, that's a different topic. AZ-ALT, that's azimuth altitude, or it's often said backwards, alt-azimuth. That is the coordinate system based on your personal frame of reference, essentially you standing in a given location on Earth looking up or down or left or right. That is not a useful metric. That is not a useful standard for conveying coordinates to other people in other locations, because for them, that same object will appear in a different place because they are looking up at a different part of the sky because we live on a round planet. Yeah. Then, here's a fun one. Galactic longitude, latitude. Galactic longitude-latitude is based on the planar distribution of the Milky Way galaxy. We live in a spiral galaxy. There is a disk-like distribution of mass, and so that's based on the galactic equator, which runs, not surprisingly, through the disk. Here's a crazy one. Supergalactic longitude-latitude, that is based on a perceived distribution of galaxies within the local group. And that is obviously not a standard you would use for conveying the position of nearby objects like planets, for example, because it would be ridiculous. You would only use that extremely large reference frame for essentially other galaxies within the local group of galaxies. So yeah, obviously all these different measurements, all these different standards, all these different reference frames have different appropriate regimes. You're not going to use these in every instance. And I just gave an example. You would never use, for example, supergalactic coordinates to tell someone where Jupiter is. That would be silly. Yeah. So I hope that answers your question. Of course, it is worth joking about the fact that this is all arbitrary. Humans decide what up and down is based on our opinion. For example, we decided that north was up. So we decided that the top of the sun was the north part, for example. That's totally arbitrary. You could say the exact opposite, and it wouldn't be wrong depending on where you are. But we have to draw the line somewhere. We have to set a few rules, don't we? Yeah. So again, I hope we learned a few things tonight. Looking at the chat. So my friends, This has been a surprisingly interesting talk. I thought this was going to be a boring one. This is all right. It seemed like there was a lot of engagement. Thank you for that. Thanks for asking questions. Thanks for making comments. I will see you guys next week. And at that time, we're going to be talking about magnetism. So we will actually discuss the motion of Earth's magnetic poles. And we're going to talk about objects in our cosmos that are far more magnetically powerful than planets, for example. We'll talk about things like magnetars, an object that has the word magnet in its name. They're so powerful. Yeah. So with that, don't miss the Great Conjunction. You still got a few days or weeks to see it. Stay curious, like, and subscribe. And I will see you next week.